ahead and get started here. The first announcement thing that you need to make sure that you know, and you've probably heard this from other people, but I just want to make sure that I've also told you, April 1st, that is next Wednesday, a week from tomorrow, is the last day to register for AP exams. Okay? So if you're intending to take any AP exam at all, you have to register by next Wednesday. Not next Thursday. Wednesday at 3 o'clock is what they said. Like, they are not going to take anything after that. Okay? So make sure you do that. Everybody that's in district has to do that at your home school. Okay? If you're out of district, you can do it at the office down here. Okay? You all, just to clarify, I think you all know this, but I just want to make sure that so people don't sign up for the wrong thing. After this course, you will be ready to take the AP Physics 1 exam. Okay? Not AP Physics 2. Don't sign up for that. You won't be ready. Not AP Physics C. You won't be ready. Okay? AP Physics 1 is what you want to sign up for. You will be ready. I think we're going to be in really good shape. I would strongly encourage you to take it. Okay? I know that some people are like, I won't need it for college, whatever. Here's the thing. You never know what's going to happen, right? You never know. Maybe the college of your dreams, the school that you go to, ends up taking the credit, or it doesn't. Maybe you end up majoring in something that is totally unrelated from what you think you're going to be majoring in, and that credit may transfer and be really helpful. Maybe the college of your dreams turns out to not be the college of your dreams, and you end up going to a different school. And my goodness, they would take the credit, right? You will be ready in May, and you'll know all this stuff in May. And it would be sad to then have to go back and take the same class again, or to take another class again to get that credit that you'll be able to earn. Does that make sense? So I'm not saying you have to take it. I'm not allowed to force you to take it anyway, but I would encourage you to take it because I think you'll be ready. Okay? Guess any questions about that at all? Anything related to that stuff? Okay. All right. Leading up to the AP exam, we've got a few more tests, and I just want to make sure that they're on your calendar, on your radar, so you know what's happening. You have the calendar for this unit, correct, in front of you, and you know that it says that we're supposed to have a test over circular motion and forces, and that forces thing will become a little more clear after today. Hold on, can I just say this let me finish the statement?
Do you have extra calendars?
If I do, they're on the wooden table, metal tray, top shelf.
Okay.
I'm not positive if there are any in there. And I can cut you one of this set if you need one. I'm just letting you know, I am not going to be here on the 3rd. I am going to have you work through material, and I think that it should be fine for you to get through that. But I don't want to give you a test the next day because I feel like if something happens, if it doesn't go well, then I don't want you to be in an ugly spot. So I'm going to make our test, so the Unit 6 test, for us will actually be on April 9th, which is that Thursday. We'll move on to new content on the 7th. I just want to make sure that if there are questions that you have on the 3rd, they're not lingering and painful. Does that make sense? So that's the first thing you need to know. Just as you're planning ahead so that you're aware, the Unit 7 test, Unit 7 is going to be really, really short. I can show you the calendar. I don't have the assignments put in yet. It's this long, though. Okay, so it's really short over circuits. That test will be on the 21st. So just as you're kind of planning through, that will be on the 21st. And then the last test you'll take will be your final. Okay? It is my intention to give you an AP final, an actual practice AP exam, mock AP exam for your physics final. Okay? Because of that, the AP physics test is 3 hours long, and we only have 85 minutes when we're here together. Okay? So I am going to ask that you come in outside of class time to do that exam. okay? I looked carefully at the calendar trying to find the best options, the best dates for that. And the thing that I came up with, and I'm hoping this works for folks, the mock AP exam. So this is your final. You can come in either the 28th or the 29th. And those dates, the 28th is the day that juniors take the ACT, and everybody else has that day off. Does that sound familiar to you? Okay. So if you're not a junior, then that day you don't have any classes at all. The 29th is just a regular school day, but it's an early out school day. I don't want to put juniors in an ugly spot where you're taking an ACT all morning and then you have to come in and take a test in the afternoon. So you do it either one of those days. It's a 3-hour exam, so it will be from 1 to 4 p.m. I'm hoping with this much warning, this much time ahead, you can find one of those 2 dates to work. If there's something that's going on those 2 days and that will not work for you, absolutely not work for you, please let me know as soon as possible so that we can come up with an alternative arrangement, okay? This is a requirement for the course, okay? So either one of those 2 dates or an alternative time. But I don't want to have, everybody taking it at all different times because that's just too much for everybody to deal with. Okay? Does that sound okay to everybody? Does that seem, are there any big red flags that people are saying that will not work at all? Okay. So I'll pass around a sheet a couple weeks before that to get sign up to know who is going to take it when, and either one of those is fine. Okay. 28th or 29th. It's a Tuesday or a Wednesday. So the Tuesday, the only people that have school are juniors and they only have it in the morning. And then Wednesday's an early out day. So everybody should be free both afternoons from school, class related stuff. Okay. Other questions about that stuff? All right. So that's all those are the 3 tests. You only have 3 more tests. That's pretty cool. Yay, we're getting close. Woohoo! Other things that are coming towards an end are labs. Let's talk a little bit about labs. Okay, so I made a very concerted effort right before spring break to get all of the labs graded, completely caught up on stuff for this class. And I am. And there were a lot of zeros. Okay? So if you didn't send me a lab, or it somehow got lost in the mail, or something happened, then I did put a 0 in there, and your grade probably is looking ugly as a result. Okay? I've had some people say, oh, but I already turned mine in, just in the last couple of days. I'm not going to go back every single day and grade labs because I'm going to tell you it takes a really long time to get myself focused to do that, okay? So here's my plan, okay? So the things I'm missing a lot of are the waves labs. So that was the standing waves lab and the beats lab and the resonance tube lab and then the angular acceleration lab, the one with the big T thing, okay? I will grade whatever I have in front of me. What's today? Tuesday? I will grade labs tomorrow after school. Does that make sense? Because I have an AP Physics C lab, so I'll be here for a little while. I'll grade labs tomorrow after school. And then after that, I'm not promising that I will get to labs again until the 10th of April. Does that make sense? So if you're desperate, if you're ineligible, if you're freaking out, oh my gosh, my mom is going to kill me, whatever, make sure that I have them by tomorrow at 12:45. Does that make sense? Okay? It will be 50% credit because it's late unless you've talked to me and there's something that actually happened. Does that make sense? Okay? After that, I will still take late labs, but I'm not going to grade them again until the 10th. I'm not going to sit here and check my email every day to make sure that I'm getting all the labs. That's just, it's not going to work, okay? A reminder, you can either put them on Infinite Campus, or you can email them, but don't email them to their school account. Don't email them to our regular Gmail account. They have to go to Carbling Labs at gmail.com. I will not look at anything that's not there or on Infinite Campus. I won't. It's too confusing. Okay. So again, I will check tomorrow. So that is 3:25 at about 1 o'clock. And then after that, I will look again on the 10th, sometime after the 10th. Okay. You can still turn them in May. I'm just not going to guarantee that I'll grade them until May 30th. Okay, so if your grade is suffering and you're freaking out, then these would be good dates to hit. Does that make sense to everybody? Okay. All right. You have one more full write-up to do for me this year. One more, that's it. Yay! That's exciting, right? You have 2 more labs to finish, the circuits labs, but those will be smaller write-ups. You've got one more full write-up, and that write-up will be for the centripetal acceleration lab. Okay, so if you were gone right before spring break on that Thursday, okay, then you missed that lab, so you need to come in and make it up. All right, because it's going to be hard to write it up without having done it. Okay, if you've done it, then you have everything, I think, because we got it through it, didn't we? I think so. I think that was the case. Okay. That lab will be due for everyone on Friday, April 3rd at 11:59 p.m. Okay. Either on Infinite Campus or via that email address. This is an individual lab write-up. And I would like all the pieces: the design, data collection and processing, and conclusion evaluation. Okay, so last one you have to do, so make it good. All right. So far so good, we okay? Okay. Before we go on and do anything else, I do want to talk a little bit about lab write-up stuff. So if you were here last time and you have your little sheet, pull it out, because there are a couple notes on the back. If you were not here and you need this sheet, raise your hand so I can give you one. Okay. So then you'll need to hold on to this, and then you need to make sure that if you are not here, you arrange a time with me as soon as possible to get this lab done. Don't arrange a time with me right this minute, but arrange it with me later today. On the back of the sheet, I put some hints about the write-up, and these were comments that I had based on the labs that I graded right before spring break. Okay? I think that most of these things are things that you should know, but I want to make sure that you have them in your head. Here's the thing, and actually look up here just for a second, because I just want to say this to you and make sure it makes sense. The purpose of a lab is to draw a conclusion. Okay? The purpose, I feel like sometimes, especially in middle school and sometimes in high school science labs, you do a lab because you're told to do it, right? And because you're just trying to check off boxes. Yes, okay, I did this. Yes, okay, I did this. But really, when you're talking about it from a scientific perspective, the purpose of a lab is to learn something, right? To draw a conclusion. And I want you to do that with this lab, okay? So the angular acceleration, or the rotational acceleration lab that we did, we were trying to show that some relationship was true. And in the centripetal force, or centripetal acceleration lab, we're trying to show that something is true. Remember, I made you think through what was going to go on what axis so that you could show that something was true. Okay? So in the data collection and processing, I put a couple notes. The analysis is intended, like I just said, to show something. Use your graph to draw conclusions. Don't just make a graph because it says to make a graph. The percent error should be based on data, on all of the data. You don't want to do a percent error for each trial. That doesn't tell you anything. You want 1% error for the entire thing. Your percent error should come from your experimental slope and compare that to the theoretical for that slope. Okay? So if you need to write any notes on there so you don't forget these things, that's an okay thing to do. I will say that the conclusion evaluations that I read for the rotational acceleration lab left a lot to be desired. And I don't mean that in a mean way, I just mean that I'm going to look for much more specific things next time, so take a look here. The conclusion evaluation section should not summarize the lab, okay? You don't need to tell me in the conclusion evaluation what you did, because that's what the rest of the lab was for, okay? This second bullet point is really important. When you write your conclusion, it should be based on what you did. It should be based on your data. If you read your conclusion and say, oh, I could have written that before I did the lab, then it's not a good conclusion. Okay? Do you understand what I'm saying? Okay? The conclusion should be based on your experience, your data. Include that experimental and expected result in the conclusion. Don't just say, oh, we found that there was a relationship. Well, duh! We think there should be but tell me the relationship. Explain to me what happened. Okay? And this last one is important too, because many of you, when you're talking about improvements, you were talking about how the equipment could be better. Well, if we had a frictionless da-da-da, and if we had the da-da-da, da-da-da, no, that's not what I'm asking. Given the equipment that you had, you should be able to get good data. I'm not like trying to sabotage your lab. I'm not trying to give you bad equipment like, oh, well, Jonathan's got to have blah, blah, blah. I'm going to give him the bad equipment. No, I'm not trying to do that. You all have sufficient equipment. When you talk about improvements, here's the secret. There are things that you can improve on to make the lab better. I know. Even you, Caleb, I know it's hard to believe. He's like, psh. Even Caleb can improve on what he's doing, right? Talk about your data collection process. What could you do differently? If I gave you the same equipment and told you to go into the lab and I locked you in here until you got within 0.2% of the actual answer, what would you do differently? That's what I want to know. Does that make sense? Okay. This is a lot of boring stuff to listen to me talk about, but do you have any questions about this before we go on? Do you have a sense based on that monologue by me of what you need to do for this next lab and how you can make it, what improvements you can make in the lab to make it better? Yeah? Any other logistical questions before we do physics? I'd rather do physics myself, but this is stuff that has to be done too. Okay. Whew. Let's do more interesting things, shall we? Yes, please. All right. When we were together the last couple of days, some of you have been here for this, some of you haven't. If you were not here on, what would that have been, a Tuesday when we did uniform circular motion, please make sure that you watch the video because it's important stuff.
You said Tuesday?
I think so. I don't remember the day that we lectured. Would that have been Tuesday? Because then we labbed on Thursday before spring break. I think that's right. We talked about this thing called uniform circular motion. I want to spend just a couple of minutes talking about it now to lead into the conversation we're going to have today. If something is undergoing uniform circular motion, what do you know about its motion? What can you tell me? What do you know?
Centripetal.
You know what?
Centripetal.
What is centripetal?
Centripetal acceleration.
It does. It results in centripetal acceleration. Absolutely. Or maybe not results in, but we know that there is, right? Because why? Because I saw it on my notes. Yeah. Let's start with the acceleration part. How do you know that it's accelerating? It's what? Changing direction. If it's changing direction, you know that because it's circular, right? Something's going in a circle. You know it's got to be changing direction. If it's changing direction, it's got to be accelerating. Yes? And that acceleration, oh my gosh, just so happens to be this weird centripetal thing. Centripetal meaning center seeking. Okay? So this always points radially inward. Jonathan, did you have a question?
No.
Okay, I just want to make sure. I saw your hand up and then I wasn't sure. If an object is accelerating, what do you know for sure? What do you know about that object? About its net force? What do you know? There has to be, right? There has to be a net force. This is like from August, yes? If it's accelerating, there has to be a net force acting, okay? So I'm just going to, let's just keep drawing little arrows here. We know that there must be a net force acting. Anytime you have a net force, it has to come from somewhere, right? Give me an example of a force that could cause centripetal acceleration. There are lots of them out there. We've talked about a few. What type of force could cause centripetal acceleration?
Friction.
Friction. Certainly. Friction can cause centripetal acceleration. Can you give me an example of a time when friction would be the thing that's causing an acceleration to cause something to go in a circle? This is like the Allison show. I'm going to let her answer one more question. Yes? Yeah! We just talked about this last time, didn't we? Yeah. When you're going around in a car, so if you're driving a car, around a curve. Think about it. Have you ever ridden in a car or driven a car? Yeah, most of you? Mm-hmm. I'm guessing all of you at some point have ridden in a car. Okay? If the car is going straight, life is good. Yeah? An object in motion is going to go in motion, right? An object, it's got velocity, but if you want it to turn, that means that you want it to what?
Accelerate.
Accelerate. It needs to go around that corner. If it's going to accelerate, that means there has to be a what acting?
Net force.
A force that's keeping it in the circle and not allowing it to go in a straight line. Does that make sense? Okay? Yeah.
Is that why it points radially?
I wouldn't say that's why, but it's a result of it. Let me say a little bit more. Maybe that'll help. So let's say that. So here's your car. It's going around this. There's the straightaway, and then it's going to go around this curve, right? So when it's over here, life is good, right? You could just be coasting, no problem. But if you were just coasting and your car gets to this point, where is it going to go?
Straight.
Yeah, like this. Oh no, and maybe there's a tree there, and that would be sad. Okay? But what do you do to avoid that from to prevent that from happening? You what? You turn the tree?
Yeah.
You turn the wheel, right? Which turns the wheels. Now, the beauty of the rubber wheels against the pavement is that there is what?
Friction.
Yeah. If you've ever driven, like maybe in January or February, and it's icy,
My tires don't
you know that the coefficient of friction does what?
drop.
Goes down. It's a little slipperier, right? And so if you're driving ridiculously, like the normal speed that you would around a curve, where are you going to go?
Off the road.
Into the tree, right? Yeah. But if you slow down,
I'm a good driver.
if you slow down, then that friction will allow you to go around the curve safely. Because the velocity matters. We're going to have a problem with that in just a second. Okay? It does. It is so true. What other forces can cause a centripetal acceleration? So it's kind of it's not as hard of a question as it may sound. Think about things that go around in circles. Just think about that. Can you imagine anything going in a circle? Whee! There's so many things that go around in circles. Something's got to keep that thing going in a circle, right? Because things don't naturally want to go in circles. They want to go in what?
Straight lines.
Right? They don't want to accelerate. They don't want to turn. So they're going to go in a straight line. Something has to pull them in.
Oh, gravity?
Think about things. I don't like when people just talk. It drives me nuts, right? You know this. Raise your hand if you got an idea of something that goes in a circle. David, go ahead.
Oh, of another force that would...
Yeah, besides friction.
Like a tension force on a string.
Tension force on a string, right? Have we seen that?
Yeah.
A little bit, right? Yo-yos and things swinging around our heads? Absolutely. Tension is another one. Okay, that's exactly what we did in that lab. The tension force keeps that object moving in a circle. What else keeps things moving in a circle? Jonathan?
Gravity?
Gravity. Can you give me an example of a time when gravity keeps things moving in a circle?
I'm going to say the moon going around the Earth, but that might be an ellipse.
Yeah, but an ellipse they all are technically ellipses, but a circle is just an ellipse, right?
Yes.
We know that, just like a square is a rectangle. What? It's true. It's true. A square is a rectangle, a circle is an ellipse, it's just a very, very specific ellipse. Okay, with an eccentricity of 1, is that right? I don't remember. Something like that. I don't remember my geometry super well. Does the moon go around the Earth?
Yes.
Yeah, in more or less a circle, right? Does the Earth go around the sun?
Yes.
Yes, in more or less a circle. Is there friction that's keeping the Earth from skidding off and hitting a tree? No. Is it a string? Is the sun like, woo, whirling the Earth around?
No.
No, there's something else that's pulling the Earth in a circle, or the moon in a circle, or our sun in a circle around what?
The sun.
Did you know that our sun is moving
Yeah.
too, right?
Isn't it around some huge
The
black
sun is
hole?
moving in a circle around the center of the galaxy, the center of the Milky Way galaxy, right? Yeah. All of that happens because of a gravitational force. Yeah. So, planetary orbits, etc. I'm going to say. And we're going to talk about that a little today and a little tomorrow, or a little next time. Anything else that you can think of that keeps things going in a circle? What else moves in circles? How many of you have been to Adventureland or a similar theme park? Do you ever move in a circle at Adventureland or a similar theme park?
The silly silo.
Yeah! They did. I'm waiting for the day when the kids that I see in front are like, the silly what? Like, what am I going to do? I don't even know. But yeah, the silly silo keeps you moving in a circle, doesn't it? Mm-hmm. What force is it that keeps you moving in that circle? What do you think? Normal force. The normal what? The normal force?
All right.
The walls push
I
you
remember that place
in.
now.
Yeah, totally. We do problems like in just a second. The normal force, absolutely.
Well, it makes sense because of gravity.
Not because of gravity, because of the normal force.
I know.
The normal force keeps you in. It keeps you in on things like the silly silo. How many of you have ridden the dragon or another similar ride like that that goes woo up in a loop, right? So those loops are not technically circles. You don't have to yell at me about that, right? They're a special name, and but the top part can be approximated as a circle. So you are going through something like uniform circular motion at the top. What keeps you in there? The seatbelt does nothing. I will tell you right now, and it's weird to think about. This is the most crazy thing. So my mom hates roller coasters. She's considered riding the Tornado. Like she's never done it, but she's considered it. Okay? I like it too. She would never, ever imagine going on the Dragon. So I told her one day, I said, like those harnesses things that come over the top of you? They don't do anything for you on the loops of the Dragon.
It's like the water.
What's that?
It's like the water.
Well, there are curves where they help.
Well, no,
but,
like
yeah.
the thing that you showed, like the.
Yeah, it's exactly the same. It's exactly like the water thing.
You would ride that without the straps on.
I don't even ride the whole thing. Because there are sometimes when you're like this, that it holds me in, right? But the loop part, it doesn't do anything. And we're going to go through a problem like it. You'll see it in just a second. The bar holds you in when you go over the hill on the Tornado, okay? So if you've ever ridden that, like, because I'm a pretty little person, when I was really little, I rode it, and like my butt would come up off the seat, right? And I was sitting there with my dad, who was a little bit bigger than me, and so like the bar only went down to his lap, and so there was like this much space, and so I'm off the seat, that much, like, oh my gosh, right? Because the bar holds you down on that part. This thing does nothing for you on the loop. Nothing for you. It's the normal force. The normal, if the track wasn't there, then you'd be cheese. Okay? If the track wasn't there, then projectile motion off, right? Okay? Kind of like cutting the string. Okay? But this thing doesn't matter. It's just like a security blanket, you know. Oh, now I feel all safe. It'll be yeah, no. The normal force also is what holds you in on looping coasters.
Nothing stops.
What's that?
So it stops at the top of the loop.
Oh yeah. But if it stops, then there's a problem.
If it stops, then you have more problems than just
It's
things
true.
not doing anything.
There's one more, but I'm going to hold off on that one more. I'm going to do a couple problems first. Okay, so here's the deal. We know that centripetal acceleration, A sub c, is equal to what? We talked about this before. We know this equation. A sub c is equal to? B squared over r, right? So there's a net force acting. If there's a net force, F net, and there's a centripetal force, then this is just m times A sub c, right? No big deal. So whatever force it is that you write as your net force is going to be equal to m times A sub c, this thing. Okay, so I'm just writing that down so you don't forget it because we're going to do a couple problems. These are mathy problems, so you will need a calculator, or I shouldn't say will, may need a calculator for these. So we'll grab one if you need one. Let's try, we're going to try 3 problems today. So this first one here is about a car on a flat curve. So this is like driving around the curve. The thing that's going to hold you in as you're going around the curve is what? What force? Friction. The friction holds you in, right? A 2,000 kilogram car rounds a corner with a radius of 45 meters. That seems big, but really if you look at a corner, like when you're going around, it's big, right? The radius is quite large. If the coefficient of static friction, seems like maybe it should be kinetic, but it's static because the wheels are moving this way, but they're not moving this way relative to the pavement, okay, is 0.82. What is the greatest speed that the car can have as it rounds the corner? I'm going to let you give that a shot. Think that through a little bit. I'm going to work on it a little bit up here too. Talk to your partners. See if you can figure it out. How fast can you go? You guys can talk out loud. It's really okay. What'd you get?
19.2.
19.0? Who do you guys think? Does that match? Yeah. So if you go 19 meters per second around this corner, then the force of friction will allow you to have that centripetal acceleration, right? If you go 18 meters per second around the corner, so less, then your centripetal acceleration will be what? Less or more?
Less.
Less. And do you remember when we said force of friction was equal to this? It wasn't really equal. What was it?
Less than or equal to.
Less than, yeah, less than or equal to, right? And so it's only going to act as much as it needs to. The maximum speed that you could go is 19 meters per second. If you go 19.2 meters per second,
We'll start skipping.
then this thing now is larger than the force of friction.
Well, not really. Oh, it is.
Yeah, good 19.02, right? So 19.2 would be greater. And so then it's going to be bigger, in which case that force of friction will not be able to hold you in anymore, and that's when you're going to go in a straight line.
So,
Okay. Yeah.
if at that speed,
Straight turn.
would you like already be like rolling though?
We're not rolled. This would just be like skidding off.
Okay, but I don't know. I was just thinking like at an earlier speed than that, your car might already start to roll, but your tires would. Still
Wait, what are you rolling about? What? Like,
Well, okay,
you must
so-
be a really crazy driver.
Look, if you're
you're in a Jeep.
Yeah,
You're in a Jeep,
I
you're
drive like a Bronco, so.
Oh, okay, so
Rolling
this is more
cars.
relevant to you. Okay.
And then so, if like I'm turning, like my car will roll while my wheels are still turning in the same direction. So wouldn't that mean that
Like literally like this way roll?
yeah, not that it's happened, but like I'm just saying that like
You would have to be going a lot faster than this.
for my car to roll.
Well, I mean, we could do the math, right? I mean, okay, so here's the deal.
That's like, you're gonna pull it.
This goes back to to rotational, or to rotational motion. Do you remember when we were talking about center of mass? And we were talking about toppling, right? So the reason that your car would roll is because the center of mass is no longer over the base of support. So if you're going on a flat road, then that wouldn't be a problem. Because the center of mass of your car, assuming that it's towards the middle, you don't have like a lot of mass on one side somehow, it's going to be in the middle, so you're going to be fine. The issue would be if you're going around a curve that's banked.
Okay.
Do you see what I'm saying?
Yeah.
Then it's going to be a little bit easier to get you to roll.
Really? Okay.
Yeah,
I thought.
I think. And that seems to make sense to me. Like I would say, I think if you're going too fast, then it's not going to matter because you're going to be cheesy either way.
I was just thinking that
Hold on, let's have one conversation, guys.
I was just thinking that in order for my car to roll,
I don't like the way you say this.
My
In order for me to get to roll, yes?
my wheels would have to be still going in the same direction that they were going the entire time, which means that they had not my velocity had not gone over 19 meters per second. That's what I was asking.
I guess, okay, so let me answer and then we'll go here. So I think, unless I'm not understanding your question, and I'm going to say that I'm a pretty conservative driver, so maybe I just haven't experienced as much fun as you have. Fun, in quotation marks. I think these are two separate issues.
Okay. Yeah.
I think. Now, so the whole issue with rolling, right, is that you have to lift up that center of mass. So in your crazy tall car with the center of mass way up here, it will be easier to get it to fall, whereas the center of mass being low will be, I mean, that's the whole reason you try and get the center of mass low, right? That's why they don't put the engines on the top, they put them down low so it's down low. Right, I could be an auto engineer, look at me. But I think that it would be really hard to get it to roll on a flat surface, given this press.
Okay.
Yeah.
Well, I was just gonna comment about if it's high enough then it will roll because the tires are going in a different direction, but the velocity of where the mass is still going
Yes.
in the
That's
same
basically-
direction.
Yes.
And that's what he was saying, so I was just...
Okay, no, yeah. But I don't think that's going to be an issue. I think it's a different question.
After it has a wider wheelbase,
Does that make sense?
Yeah.
Yeah. Jordan?
So, with like speed limits and stuff,
Yes.
they do something kind of like this.
This is exactly what they do. Yeah.
Okay.
So like when you're driving from Polk City to Allman, right, and you go the curvy way,
Yeah.
okay? So we just have to have a moment here. If you go the curvy way, they're banked curves, right? And they're banked because you can drive on them when it's icy and you still are okay. Because in that case, then the normal force is pushing you in as well.
Yeah.
But, so when they bank those curves, they bank them to a certain degree so that they can do that. But even in this case, they choose speed limits such that you are moving at a safe speed.
But doesn't it like depend on the mass of your car?
Does it depend on the mass of the car?
No.
No, it doesn't. It seems like it should, right?
Yeah.
But it doesn't, which is weird. Yeah. Questions? Go.
What is the radius between
What do you mean?
like with the whole with the car question? Where does the radius come in?
Into flipping the car, it really doesn't. I don't know.
I was just curious. I was like,
I don't know for sure because I need some more like, I need to analyze that a little bit more. Yeah. I don't think I want to.
You need to ride with him someday, see how he drives.
No, I'm frightened. I'll ride behind him. Or I'll put a camera in the car. I'm not going to ride with him. That sounds awful. Okay. Couple more problems to work on. Okay. So we mentioned that not only does it keep us in our circle when we're going around the circle. We did this problem already. We're going to get here next time. Let's go back to the normal force now. The silly silo and looping coaster. We're going to do looping coasters first. This problem is not really about a looping coaster, but I just like it. I think it's kind of funny. I mostly just like the picture. So in 1901, that's a little while ago, circus performer named Daredevil Diablo, which is an awesome name, introduced the stunt of riding a bicycle in a loop-the-loop. Sounds like a good plan. Okay, so he's not strapped in, but he can do it. It's okay, as long as the loop is continuous, right? If the loop goes away here, then there's a problem, right? But as long as that loop is there, he's okay. Assuming that the loop is a circle with a radius of 2.7 meters, what is the least speed v that he could have at the top and still remain in contact? So this is kind of like the water, right? When I had David sitting down there and I spun the water, I couldn't spin it at any speed, right? Because at some point it would fall out. There was a minimum speed that I could spin it at and still be safe. Or keep him safe, I guess. I was just standing there, whatever. But there's a minimum speed that he can be going up there and still be okay. So the first thing I would do if I were trying to solve this problem would be to maybe draw a free body diagram of him at the top and write an F-net equation there. I'm going to let you do that first, and then we will touch base. What's pushing on him?
Normal force is keeping it from going outside the loop.
Normal force? Do you guys agree a normal force is pushing? Which way is the normal force going?
Down.
Down. Yeah. Turn that off, whatever that is. I don't know what it is, but I want it off. So this is the force of the track on Allo Daredevil Diablo going down that way, and that's a normal force. Okay? Anything else acting on Allo Daredevil Diablo? Gravity, right? Which way is gravity going?
Down.
Down. This should look very similar to you to the free body diagram that we drew of the water at the top. Do you remember? And it was a little bit weird, but that's all that's acting. So we've got F of the earth on Allo Daredevil Diablo, and that is FG. Anything else acting on him when he's up there? Is there any force pushing him up? No, there's not. There's not, right? So we got F net equals Fn plus FG is equal to MA, but we know that he's going in a circle, so I'm just going to go ahead and write that as V squared over R. Now, FG is going to be some value, right? His mass times 9.81. Do you agree?
Yes.
And his mass is going to stay constant. The radius is constant. Is the velocity a set value? No, I mean, it kind of, that's what they're asking for, right? So, like, there could be different things. What about the normal force?
The normal force is going to be the same.
The same what?
It's going to be the same value the entire time.
Will it? Always?
I believe it will be.
What about the force of friction?
What about friction? Is friction acting in this case?
No, it's not stated that it's acting still.
There's no friction acting here. So if I take an object, you guys have, I'm sure, done this at some point, when you've been swinging something in a circle, in a horizontal circle, if you swing it in a slow circle, if you swing it too slowly, what happens at the very top?
It slows down.
It starts to fall down, right? It kind of goes slack. So what is going on with the tension there?
The tension force is not equal to the force, is not great enough to counteract gravity. Oh, no, that's wrong.
Try again.
That would be a different part.
Try again. The tension what?
The tension force is a work grain.
What's happening to the tension force? It's going to what? What value?
0.
0, right? If I spin this thing really, really, really fast, okay, you're like, oh my gosh, because if I spin it too fast, what's going to happen?
The string is going to snap.
The string is going to snap, free, boom, projectile motion, right? Okay? In that case, so what do you know about the tension as I spin it faster and faster?
The tension force increases.
It's getting bigger and bigger. Look at this. Pretend this is tension for a second. Pretend this is a yo-yo. As the velocity gets bigger, what happens to the tension force? It gets bigger and bigger and bigger, right? Because gravity, is that going to change? No. So the slower that I move it, the smaller that tension force is. Okay? Same thing here. If he goes really fast, okay, then the normal force is going to be big. But the slower he goes, what happens to the normal force? Gets smaller and smaller. And if we ask what the least speed is, I want the smallest value here. What's the smallest value of this going to be? 0. That's as little as it can be, right? It's not going to go negative. That doesn't make any sense. So the smallest value for V is going to be when Fn equals 0. Okay? So set Fn equal to 0 and then solve for V. Does his mass matter?
Nope.
That's nice. How fast does he have to be going? The slowest possible speed. Did you check with your neighbors yet?
Oh,
Check with them first.
checked and it checks out.
What'd you guys get?
5.14.
It's weird, right? It's weird. So, when you go around that loop, when you're riding the dragon, you're being pushed, right? You're not being pushed out, but the seat is pushing you in. Okay, the seat is pushing you down, okay? Because you're going fast enough for the seat pushing you down. The minimum speed that roller coaster designer had to make it, in order so that you didn't fall, right, and so that you made it around the loop and they didn't have to like pay your insurance company a whole lot, your family a whole lot of money, right, was for the normal force to be 0. So the slower you go around that loop, the smaller that value will be. Another way to think about it, have you guys ever ridden on the teacups or on the tilt-a-whirl or on one of those like horizontally rides?
Yes.
Right? So, or like any of those, the scrambler ride, you know how it feels like you're being pushed out? Here's my question for you. Are you being pushed out?
No.
No. You're not being pushed out, you're actually being pushed where? In. If the walls of those rides were not there, where would you go?
Projectile motion.
Straight line, right? And then zoom, right? And boom, splat, bad news, okay? So the walls are actually pushing you in. At the beginning of those rides, the teacups or the scrambler, depending on how, dangerous you like to live your life, okay? At the beginning, the walls aren't pushing in on you very much, right? The normal force is very, very small. But the faster you go, the more those walls are pushing in on you. So the normal force keeps getting higher and higher. It's the same deal here. Does that make a little more sense, maybe? We doing okay? Okay. One more. We have to, pay honor to the silly silo, the sad story here. So, let's talk about this silly silo. How many of you have ridden the silly silo or something similar? How many of you are completely frightened to ride the silly silo or something similar? Yes. Now, here's my question. Chris, you're saying, I hate this thing. It sounds like the most horrible thing. Have you actually seen what happens? Or have you just heard
All I
stories?
know is that it makes me sick.
Okay. Yeah, so the really sad story is I had a friend that came to Adventureland. He hates roller coasters. We were there on one of those days where, there was nobody there. It probably was raining or something. And we'd ridden all the roller coasters and he'd ridden them with us. And then we're like, we're going to ride the tornado one more time, just one more time. And he's like, yeah, okay. Like, he had just eaten a funnel cake, and he's like, I can't do this. So he's like, I'll just wait for you at the end. He's a tall, redhead guy, right? And so we went and rode the tornado. We expected to see Jeremy out and right out there. And we got off. Like, that was so fun. We looked for him, and he's really hard to miss. Like, where is he? And then we looked up, and what was right next to the tornado was the silly silo. And he was standing over the edge. Because for some reason, this brilliant guy had decided that instead of riding the tornado, he'd just go ride the silly silo instead to wait while he was waiting. Like, not a good plan, right? Chris is like, I'm not going to do that either. Like, no! So for those of you that haven't ridden this wonderfully awesome ride, or perhaps, less than ideal for your tummy, okay? What happens? You go in this room, right? What does the room look like?
It's a cylinder.
It's a cylinder, right? It's got a floor, no ceiling. You can wave at the people that are watching you, and you stand there. That's pretty exciting.
It is.
And then what happens?
The cylinder starts to rotate.
It starts to spin, okay? And as it starts to spin, you're like, oh, that's fun. And if you just watch the person across from you, life is good. You don't have any idea you're spinning, right?
Then?
You're just in this nice little space. Life is good, and it keeps spinning faster and faster and faster, okay? As it's spinning faster and faster and faster, you are now experiencing, well, not right away uniform because you're accelerating, but eventually uniform circular motion, right? You're going in a circle. You are now the object going in the circle, okay? Do you want to go in a circle? Do you want to be accelerated?
No.
No, you want to go in a straight line. Thank goodness the walls are there, okay? So the walls are there to keep you from going in a straight line. Actually, here's the funny thing. Silly silo, salad spinner, same thing. Okay, have you ever seen a salad spinner? Or if you've ever looked at like a washing machine, same thing, right? The walls of the washing machine hold your clothes in, but they have holes, right? The holes are big enough to let what through?
Water.
The water. So the water is able to continue in a straight line. It doesn't have that normal force pushing on it. Does that make sense? Same thing, same principle. So here you go, you're in this thing, you're standing there, and all of a sudden it feels like what's happening?
You're being pressed into the wall.
Right, like you're being stuck to the wall. Now, is there anybody that's actually pushing you against the wall?
No.
No, it's not like they have employees that are like Like, that would be really creepy and weird. No. Nothing is pushing you out. Nothing is pushing you out. In fact, what is actually happening?
The wall is pushing you.
The wall is pushing you in. That's nice. Because then after that, then they hit that other button. And that other button does what? Yeah, the floor leaves you, right? And so then you're like just sticking to the wall, and there's nothing below you. But you don't what usually?
Fall.
Except that the last time I wrote it, right before they closed it, I think the reason they closed it because the motor wasn't going fast enough because I did not stick it. I was really unhappy. What the heck? It was because they weren't going fast enough. Stupid thing. Right, so you're sticking to the wall. Let's think about what is going on here. Draw a picture for me, a free body diagram
Of someone.
of you. We're doing a side view. Here's the wall. Here's the floor. These are your feet. Free body diagram of you standing or sticking, not really sticking, but against the wall of the silly silo. Draw the free body diagram. Go, go, go. What forces are acting?
So good.
With a big smile on your face. It looks like a Pez dispenser. It does, doesn't it?
It does.
Yeah. All right.
I can never figure out how to get those things to work.
Oh, that you just open the mouth? The candy comes out. I think. Okay, what forces you got? Let's see. Jason, you got a force? The what force? Hold on. Whoa.
Normal force.
The normal force. Normal force. Natural. I don't know why people say that. I don't know what it feels. Pushing which way? Where does the normal force push?
And
In, but
Is it in or out? There's
It's
choices.
it's in. I don't know why I said out. I was being stupid.
You want to think it pushes out, right? Because when you're standing there, it feels like something's pushing you out. But there's nothing there pushing you out. There's not a person pushing you out. There's not like a string pulling you out. There's not, no, you're not being pushed out, right? It feels like it. But you're not. It's just because you're going in a circle. The normal force is pushing this way. So the force of the wall on you is pulling you in, pushing you in. That's weird. But we know, if you look back at your notes from September, that the normal force always acts perpendicular to the surface, right? And if the surface is right there, then it's got to be going that way. That's the only way it can make sense to go. What else? What else you got?
Gravity.
Is gravity acting?
yes.
I hope so. It's not like they transport you somewhere outer space with there's very little gravity. No. Of course, gravity's acting. It's going this way, right? Force of the earth on you, Fg. What else?
Oh.
What's that? Friction. Friction going which way? Up. Friction always acts what? There are two things we know about friction.
Opposite.
Opposite of?
Motion.
Opposite of where the motion would go, and it always acts what to the surface? Parallel to the surface. Yeah. So it's going this way. So this is the force of the wall on you, parallel, so that's FF. So why don't you fall down? Why don't you slide down?
Because of the normal force.
Not because of the normal force is pulling you
Because of the
in.
friction.
The force
Because
of
friction is holding you up.
Now it's really fun to push up.
Weird. So when I said that when I was writing it, they weren't going fast enough, here's the thing. It wasn't going fast enough, so the normal force wasn't high enough. And because the normal force wasn't high enough, the frictional force wasn't
High enough.
high enough, and so I slid down. Sad day. Okay? I want you to figure out here the minimum speed that the cylinder needs to go so that I don't fall when the floor drops out. The details are that the coefficient of static friction is 0.4, and the cylinder has a radius of 2.1 meters. Okay? You have to write down some F-net equations in order to figure that out. Give it a shot. I bet you can do it. Does the mass of the person matter?
No.
No, which is good. Because my Uncle Howard was not a small man, and he would ride this. And I was little when I rode this for the first time, and I would ride right next to him, and neither of us fell down. Okay? Yeah.
But since like the coefficient of friction does matter, does that mean that like based on the type of clothing you were wearing, how much you would stick to the wall?
Yes. Yes. So if you were wearing like your rain slicker, I'm trying to think of something that would be super slippery, right? Or I don't know what.
A wetsuit?
A wetsuit. Yeah, if you were wearing a wetsuit to Adventureland, then you would slide down more easily than would someone wearing a what?
Velcro.
Velcro. Yes. Yes. So it's an insurance game, right? So when they decide how fast this thing actually needs to move, they're going to make it move a little bit faster than the minimum, so that even somebody wearing that wetsuit is not going to slide down, right? Because they're and if you remember, I think that in the actual, so it was kind of like a sticky material. It's like
It was like,
Yeah.
It was like
it wasn't sticky, but yeah. Like there was a high coefficient of friction.
Yeah.
Huh. It's like they planned that or something. So V is equal to what? Like the square root of GR over mu? What did you get for a V?
How does that make you feel?
Did you get a value?
7.2.
7.2?
That's what I got.
Yeah, 7.2.
All right. Are we doing okay? Okay. Is this making sense? We're doing like this is sitting okay in your brain? We know how to apply this? Okay. I'm going to go back to that list about uniform circular motion. There was one more that I wanted to add here. I don't know if you remember way back in the day when we were talking about forces. We said that there were some forces that were contact forces, and then we said that some forces were field forces. Do you remember that?
Oh.
Like way back. So we've been talking about contact forces for ages. Next time, hold on, let me finish my statement. Thanks. We're going to talk more about some field forces. One of them is this gravity thing. Okay, so this is a contact force. This is contact, and the normal force obviously is contact. Gravity is a non-contact force. It's a field force. We're going to talk more about this, like I said, soon. There's another field force that we talk about some, and that causes circular motion, but not on such a large scale as something like a planetary orbit. My chemistry friends, this may be something that fits into your brains a little bit more, yeah? Magnets, and there's one more piece to it. There are two pieces that go together. Magnets and, what's an atom made of? Well, this is not a trick question.
Protons.
Electrons, protons, and neutrons, right? And what's their, is it just a big mass of charged particles?
No.
No, there's a what in the middle?
But
A nucleus that's got a what charge?
positive.
Positive charge, and then there's what that goes around it?
Electrons.
Electrons, right? And those electrons, in a simple model, orbit the positively charged nucleus. Okay? So the that electric force, also causes circular motion. So I just want to throw that out there because that's the last part of what we're going to do this unit, is talking about, we're talking about the electric part of electromagnetism. So electromagnetism is what leads to electrons orbiting the nucleus. And it also leads to, I was asking Mrs. Kasuga last block, because I didn't know how much you guys talk about it in chemistry. I said, I think you guys talk about this, right? Mass spectrometer? She's like, yeah, I mention it. So if you've heard the phrase mass spectrometer before, a mass spectrometer, you don't talk about this in chemistry, but it uses magnetism to get those ions to curve, to exhibit uniform circular motion as well. So just, you know. If you take AP Physics 2 with me, we'll talk about this. I'll show you how it works. It'll be a beautiful thing. Okay, so this is also a field force. I'm going to talk about that next time too, or soon too. We good here? That's a more complete version. It's not all of the forces that can act, but it's many of them. Now, we need to have a conversation. This sounds really like deep. I need to have a conversation with you. This is something, I was looking through my sheet that has all of the stuff that you need to know. And there's a whole, there are 3 of the enduring understandings, like the big deal ones, that talk about something that I find to be pretty silly. But if it mentions it 3 times, and then it also mentions it in the sheets that I gave you, in the learning objectives twice, it's probably something you need to know. So I'm going to give you my 10-minute spiel. Are you ready? Okay. Gravity. So we're going to the gravitational force. We're going to focus on gravity. We're going to talk about gravity later and how it works. We're going to talk about that next time. But the gravitational force acts between any 2 what? What do they have to have in order for gravity to act?
Mass.
They have to have mass. Okay? Mass is this idea that we kind of take for granted sometimes. I think I asked you at the beginning of the year, what's mass? And we kind of stumbled around some sort of definition of mass. Maybe said how much stuff something has, and that's kind of a terrible definition when you really come down to it, let's be honest. But it works, right? Here's the thing. There are technically 2 fundamentally different definitions for mass. Okay? So I'm going to tell you what they are. The 2 definitions for mass number 1, or maybe not even definitions, types, really. 2 types, which seems even weirder. Number 1 is gravitational mass. Objects have gravitational mass. That's why there's a force between the Earth and us, right? When you draw a free body diagram of yourself, you're always going to say the force of the Earth on you. And the reason you have that is because of gravitational mass. You have mass. Okay, you are massive. I'm not saying you need to lose weight. You have mass. It's true. Okay? If you were to measure your gravitational mass, how would you do that? Or how would I measure the mass of my yo-yo? How would I do that?
Put it on an electronic balance.
Put it on electronic balance. How else could I do it? What if I don't have any electronic balances? No electricity. How else could I do it? What's that? Yeah, triple beam balance, right? You're going to use a balance. And basically what you're doing when you're measuring gravitational mass is that you're comparing the force of gravity of an unknown mass to the force of gravity of a known mass. So a triple beam balance, when you move those little bars over, you're really just trying to get them to even out, right? And then the secret is that it actually uses torque, right? Because you're not changing the amount of mass, but you're changing where that mass exists. So maybe I should have a lab where you have to build a triple beam balance. That would be cool. Because that's all you'd be doing, right? Would be trying to find how far away each of those things needs to be so that the torque is equal, and that's how they balance. And that's really all you're doing. You're comparing the force of gravity of something you don't know to the force of gravity of something you do know. And when they're equal, then by golly, these have got to have the same mass. Does that make sense? Okay? You do the same thing when you use like a scale like this. It's just been calibrated already. Okay? It's the same deal. This is a known mass. In order to do this, you're going to use some sort of balance. And when you do this, and this seems kind of obvious perhaps, but it's something that they want you to know, so I'm going to let you know it for sure. When you measure gravitational mass, you measure it at rest. Right? You're not going to measure the gravitational mass of something while you're moving it or while it's accelerating. It doesn't make sense, right? You're going to put it on a balance. You're going to watch where they balance out, right? You're not going to try and do that while it's moving. Okay? There you go. Gravitational mass. Does that make sense? Pretty straightforward. Okay? The second type of mass is called inertial mass. You've heard the word inertia before. I don't use it very much. Inertia means the tendency for an object to not want to change its state of motion. Okay? Inertial mass is defined by Newton's law. Newton's first and second law. We remember that that's F equals ma. Inertial mass is measured by applying some known force to an object and then measuring its acceleration. Does that make sense? You apply some force and you measure its acceleration and you divide them and you can find the mass. Okay.
Whoa.
I know, right? Like you just divide and it's there. So I'm going to write that down so I don't forget. Apply a known force to a mass and then measure the acceleration. Okay? Hopefully it makes sense that if you're going to do this, you have to get the thing to accelerate, because if you have 0 here and 0 here, that's not going to tell you anything about this. So that means that in order to measure inertial mass, the object has to be what? Accelerating. Unlike this one where you're measuring it at rest. So this one is measured while in motion. Okay? And that's what this one is. So this one's defined by F equals ma. That one's defined like with a gravitational force. Is that okay? Now here's the kicker. This is my favorite part. And this is why I don't understand why they get cranky about it and why we have to talk about it and all of this sort of thing. You've got two different types of mass. Gravitational mass and inertial mass. You measure them differently, and that's the thing you want to know. They are measured differently. I would write that down somewhere. They are measured differently. Let me write that nicely. Okay? But when it all comes down to it, and you say, okay, well, you're measuring it differently, so what's the difference? The answer is, there isn't one. All physics that we understand, and not just the simple, like, basic Newton's laws physics, general relativity, string theory, like all of the ridiculous physics that exists, cannot find a difference between gravitational mass and inertial mass. So it's kind of dumb, in my opinion, to get hung up on it, right? They're the same darn thing, you're just measuring them different ways. That's really all it is. So the things you need to know are how to measure them, and that they are, in fact, the same thing. So I don't think that there would be a free response question about inertial mass and gravitational mass. I don't have any idea what kind of question they would ask you, except how would you measure them? But now you can answer that question, right? The thing that they might ask, though, is what is the difference? And you would say that there is no difference. Okay? There's no difference except how you measure it. Got it? What's the difference between gravitational mass and inertial mass?
None, except for measuring method.
Right. You measure them differently. That's it. And that's the totally anticlimactic way that we're going to end today. So you're welcome for that. If you need to schedule a lab with me, why don't you come up and do that right now so we don't forget?